Thank you very much. So my sort of historical involvement in deep water comes about from a brief spell in the Gulf of Mexico with a former independent, Enterprise Oil. So that was my first $100 million well. And then more recently, BG has quite a big deep water portfolio in Brazil with Petrobras in Egypt and more recently in Tanzania. So I guess one of the last things I did at BG was look at a Petrobras appraisal well in the subsalt, which was my first $300 million well. And that was the AFE, not the outturn. So an expensive place to do business. So what I was going to talk about a little bit was some definitions, a little bit of data, and then talk more broadly about disappointments. Trying to avoid some of the disappointments. And I think you'll see some themes that are pretty common to the first two presentations you've seen today. And then a few personal reflections. There's a lot of focus on pace and front-end loading, and I certainly have some sympathies about that. But I have another insight which I'd like to bring at the end of the discussion and see how much that lands with you. I've collected a bit of data on deep water fields. There's a bit of a caveat emptor. For those of you who went to proper schools, you'll know what that means. For those who went to comprehensives, that means take it with a bit of a pinch of salt. So I've collected a bit of data and tried to present some historical trends on deep water. So the only thing we know about the data is that it's wrong by definition. The issue is not is it wrong, the issue is it useful. So some stuff is missing. I'm kind of a bit out of date on what's happening in the subsalt. Mozambique is, 5 years ago it was 20 TCF, now it's 200 TCF, whatever. Some of the regions don't really report associated gas very well, and some of the smaller discoveries in the Gulf of Mexico are missing. So if you look at some of this data and say, well, that's not quite right, then you're probably right. Again, the way the data's been presented, some assets sort of have shallow opportunities and deep water opportunities lumped together. So there's potentially volumes in this data set that come from shallower opportunities. So what is it? There's a range of industry definitions, but generally looking at sort of 400 or 500 meters for deep water, 1,500 meters, 2,000 meters for ultra deep water. So if we just take those definitions and collect up all the assets, we're looking at something like 40 billion barrels of oil, about 120 TCF of gas, so something like 60 billion barrels of resource. And I use that word carefully because some of it will be resources, it won't all be reserves, of which about 44 is remaining. Now these numbers are probably an underestimate. I did this analysis a year or so ago. So one thing that sticks out straight away is the sort of immaturity of the deep water play. And when you look at some players, the EUR and the reserves are almost the same. They've produced almost nothing out of their deep water portfolio. A lot of recent developments. So this learning about how reservoirs are going to behave during the actual production phase is, we're learning a lot, and I think we're going to learn quite a lot more quite quickly. Historically and forward projections, you're starting to get towards $1 trillion of Capex. And some of these numbers are historical numbers, so they're not money, they're not normalized in terms of inflation. I just had a quick look through all of the projects and pulled out the sort of P10, P50, P90 resource and development Capex. So you're generally looking at quite large opportunities here. The P50 is coming in at about 350 MMBOE. The P50 Capex is coming in at $4 billion, that sort of thing. So these are big opportunities, and they generally need to be big opportunities to make the economics work. You can't do these projects with small resource base. Simply can't afford the capital. This is a bit of data courtesy of WoodMac. So one question is, why is deep water of interest? And it's sort of obvious. There's a large resource base, but WoodMac produce a nice summary of key discoveries in each calendar year. So this is from 2010. The data is plotted, in terms of ultra deep, deep, conventional, and onshore. So you can clearly see that there's a lot happening in the ultra deep. And the reason this is a big focus is it's basically what the IOCs can get their hands on. why are we doing deep water and unconventional and Arctic and thermal? Well, it's basically because we're not getting our hands on the conventional resources in the Middle East, in Iran, in Saudi, places like that. And if you look at those discoveries, this is the little table of the top 10 discoveries, and we won't go through the table in great detail, but if I strike out the things that were not accessible to IOCs, a couple of big discoveries in Iran, actually 7 of the top 10 discoveries were in deep water. And three of those 10 were not available to conventional IOCs. So 7 out of 7 of the top discoveries in 2010 were in deep or ultra deep water. So if you want to find a big field, the data suggests you really need to be looking in deep water. In fact, you probably need to be looking in ultra deep water, and I'll show that later on. This is the data just presented by sort of geography. So this is EUR, this isn't remaining reserves. Big dominant position in Africa, big position in South America, which is basically Brazil, quite a bit of gas in Southeast Asia. North America, this is Gulf of Mexico, and then Europe, quite a big gas position in Europe. And then we've got the Reliance D6 block, which I'll talk about later on. So it's pretty focused in a few key areas. This is the same data, but presented by country. So again, probably not telling anybody anything they don't know already, but Angola, Brazil, Nigeria, Gulf of Mexico, Australia, Egypt. Pretty dominant in sort of 6 key countries, and then a long tail. Not a huge position in the UK, Western Britain as it's described here. And what you can see is, again, how immature some of these portfolios are. So now this data is a few years out of date, but I don't think it's going to have changed hugely. So the difference between the gross ultimate recovery and the reserves/resources is not that large. So quite an immature portfolio globally. This rather colourful slide plots the sort of discovered reserves against discovery year, and it's coded by sort of geographical area. So sort of started off a little bit in Malaysia, perhaps a little bit inaccurate here. This is where we've got some assets that have got shallow water and deep water, so possibly not very realistic. But really started happening properly in Brazil, Petrobras, Gulf of Mexico. We're talking about the 80s here. Then an absolute explosion of activity in Angola and Nigeria. So the reds, Africa. Then actually a pretty quiet phase, and then again another explosion of activity. And now we're not on the west coast of Africa. We're on the east coast of Africa. We're in Mozambique and Tanzania to some extent, plus a bit of a contribution from Tullow to some extent. If we look at that same graph and look at it by hydrocarbon phase, the thing to remember about this data is what you're seeing here is you're seeing the fields that are happening. You're not really seeing the fields that aren't happening. So absolutely dominated by oil phase in the early part. No perception that anybody would go exploring for gas, in the 80s in the deep water. No way to make those projects work. Then we're seeing more interest in gas in the 90s, and then we're seeing a lot of gas, again, pretty dominated by these big Mozambique discoveries that have happened in the last 4 years or so. So gas becoming much, much more important, LNG becoming a way to monetize gas more recently. This is an interesting chart from my perception. It just splits the same data again into ultra deep and deep. I gave this a subset of this talk at a Deepwater presentation SPE conference in Trinidad a couple of years ago, and the title of the conference was Getting into Deep Water. And for those of you familiar with Trinidad, they're having their sort of first deep water licensing round, awarding a number of blocks. And my sort of takeaway from this was that actually, really, it's not a question of getting into deep water, it's probably a question of getting into ultra deep water. So again, most of the large discoveries are being made in 1,500 meters plus. So you might want to think quite how aggressive you are in terms of water depth when you put your exploration strategy together. This is a bit of data, again, looking at the maturity of all this resource base. So what I have here is FIP, field in production, field under development. So this is post FID. If that's enough three-letter acronyms for today, then I'll stop. So basically fields that have been sanctioned and are actively under development. And then FAD, field awaiting development. Or, as I've noted up here, perhaps awaiting development, possibly stranded resource or long expectations of development timescales. And what you can clearly see in here is it's not easy on all occasions to progress gas. You can see a big, the stuff in production is predominantly oil, and the stuff people are scratching their heads about is predominantly gas. So quite a bit of stranded gas, difficult to monetize, reaching critical mass for LNG, lack of domestic market, those sorts of challenges. This is Capex, plotted against year of first production. So I haven't bothered allocating the Capex to the actual execution. I've just tried to reference it in general time. And again, what you can see is, huge amount of activity in the previous decade, mainly associated with, Angola, basically. A little bit quiet, and then another projected phase. So here we're looking at 2010 onwards. So this spike isn't real. This is one project that would have spent some money over 4 or 5 years. But if you look at that data, it's sort of saying about 20 billion a year, which is quite a lot of money, being spent in deep water developments globally. Last slide in terms of data. This is Capex per BOE versus year of first production. Now, the way the data is presented, it's all normalized at a notional inflation. So if I take a project from 1960 and a project from 2010, it's rather hard to compare the costs. So if I say inflation is 2.5%, I'll take that 1960 project, I'll inflate it at 2.5% per annum, and I'll try to normalize it. So these costs have inflation, in a very notional sense, taken out of them. But what you can clearly see is we're obviously not getting our inflation right because this curve here, and the green is the oil, for those of you that used to work for Shell, this curve here is running at about 3 or 4% ahead of the inherent inflation assumed of 2.5%. But what you're seeing also is that the gas projects here are coming in at a much lower cost base. Now, when I worked at BG, we used to have interesting conversations about, was gas cheap to develop? And actually my perception is that gas isn't particularly cheap to develop. It's just that the projects that you can afford to develop have to be cheaper. There's two dimensions to looking at this cost base. I don't believe that gas projects are intrinsically cheaper. It's just because I have, the costs associated with LNG, because I have a relatively low commodity price in general, because I have a 20-year LNG project on plateau, which actually means that, really half of these reserves have no value because I just discounted them to death. So these gas projects have to be cheap. And they're running in the sort of, $5, $10, $15 per BOE basis. And my oil projects are running up at, 15 plus. So lots of evidence of rampant inflation in the oil and gas industry. It'd be interesting to plot the salaries of petroleum engineers on this graph. See whether they've stayed ahead of 2.5% as well. Same sort of data. This is plotting cost against field size. Now, because the historical data is really a bit irrelevant, I've only looked at relatively recent developments here. So it's sort of things in the last 10 years. I haven't gone back to the 1980s. So you've got the same distribution, you've got the same sort of range associated with the sort of norms that you expect. Oil is coming in at sort of 5 to 30, gas is coming in at 2 to 10. But the really, really important point on this graph is there is absolutely no relationship between the size of the field and the development capex. So don't expect your field that is twice as big to have a much, much better rate of return. And the reasons for this are quite simple. Deep water projects are dominated by wells, by the costs of drilling wells and the costs of subsea architecture. So if you can recover 25 MMBOE per well, and your field is twice the size, then I'm afraid you need to spend pretty much twice as much money as the smaller project. So there's very limited economies of scale in large projects, large deep water projects. Whereas, of course, if I have a conventional facility, you know, if I have a jacket and a facility and I suddenly decide I've got another reservoir beneath me and I wish to double the reserve space, I have tremendous economies of scale. So, and I think this is something that we saw earlier in Mike's presentation where he plotted internal rate of return against field size. And there are issues about the tax regime as well. Obviously, if I double my field size, I'm probably giving the government a little bit more of the share. But you're not really seeing rates of return on these big deep water projects in general improve dramatically as the fields get bigger. And I think the data sort of shows that. This is something on schedule, and again, very similar to some comments that Mike made. So this is time from discovery to first production in years, plotted in this axis against the year of discovery, I think. And what you can see is, you know, there's real evidence of, you know, a significant improvement in industry performance. People are getting quicker. You've got quite a big clump here of gas projects that really took quite a long time to get going. You're looking at 10 to 25 years to get these projects going. But things improving later, more recently. I suspect when the exploration case for these opportunities was put together, I very much doubt they had 25 years to first production on their radar screen, because pretty much by definition you would never drill such a well, because the EMV of such an opportunity simply wouldn't warrant drilling a well. So timescales seem to be getting better, gas generally slower. So just a summary of the data. Deep water, why are we doing it? My description is it's the IOC playground. It's the bit where the IOC's technical capabilities and access to acreage can create opportunity for them. That's why they're pursuing it. And obviously there's quite a bit of materiality. Something like 60 billion barrels gross ultimate, undoubtedly wrong, this number. I think if you look at it today, it'll be bigger. And a relatively immature portfolio, some key countries, and then probably 20 plus billion a year being spent on development, by which I mean facilities and wells. So the next part of the presentation was just to look at some sort of reflections on a few fields I've had the opportunity to interact with. We saw a similar sort of stage gate process earlier. We're looking at exploration, appraisal, the concept selection definition phase, and then we're into first production. And I wanted to think a little bit about appraisal, resource definition, project execution, and reservoir management. So this first slide, it sort of reinforces a point I made earlier, again, courtesy of Wood Mackenzie. So this was Capex spend in Angola split between facilities, subsea, sorry, the screen on here is rather small, so facilities, subsea, and drilling. And the bottom line is 75% of your money is not going on facilities, it's going on wells and subsea. So this is some interesting work that Wood Mackenzie did quite a while ago. It's a bit out of date now, but it makes a very strong point. This was when the Mozambique discoveries were coming in. They looked at the performance of that Mozambique portfolio as a function of size. And they looked at different well cases. So they said, you know, what happens if a well recovers 100 BCF? What happens if a well recovers 200 BCF? And how big is the opportunity? Now, the numbers on the bottom here, model field size from 1 to 6, they're sort of missing a 0 now in the context of what we know is going on in Mozambique. But I think the point is valid, is that what they show here is the net back gas price to break even on a project, achieve a sort of 10% rate of return, as a function of the field size in this axis, and then how much a well is going to deliver. And the interesting point is that if your well delivers 100 BCF, it doesn't matter whether your field is 1, 2, 4, or 6 TCF. You're really going to struggle to make that project work. And it's back to this issue about the development costs are dominated by wells, by the drilling of the wells, the completion, and the subsea architecture. And if you need twice as many wells, you pretty much just doubled the capex of the project, which could make your economics look quite challenging. And this sort of raises the point about historical benchmarking, and this is from another source, but I've kind of looked at these numbers myself. When you look at offshore projects that get developed, you're looking at 50 BCF a well in the low case, up to Ormen Lange. Ormen Lange was it's a sort of designed in heaven reservoir, I think is probably the best description of it. So they're achieving 450 BCF per development well. So, quite a big range in outturn, and trying to understand where you are on that spectrum is going to be really critical to your project economics. And I think the difficulty is that we've heard discussion this morning about, more appraisal, but appraisal wells are generally very good at defining static volumes. They're often not particularly good at defining dynamic performance, compartmentalization, long-term effective permeability. And actually, the bit that bites you in the deep water is not really knowing how big the field is, but knowing about well performance. So I'm not clear that conventional appraisal, more of it always, is going to help you a lot. You might define the static resource base. You might... Is there a swallow in the room? You might define the static resource base a lot better. It may not get you where you need to be. There's been a lot about IPA. I promise, I've never worked for IPA. I didn't know what they were going to say this morning, but there's a pretty simple conclusion which has already been made adequately, is mega projects, $1 billion or maybe $1.5 billion in today's money. Deep water projects are almost always mega projects. IPA has, adequately demonstrated to us all that the E&P projects don't do very well, but mega projects do a lot worse. So, it's I don't need to emphasize that anymore, because it was pretty thoroughly discussed this morning. So it's very hard to find out about the things that go wrong. The industry is very good at, you'll find lots of papers about this success, that technology. It's not easy to find things that go wrong, find out about things that go wrong, although there are plenty of things that do go wrong. This is a rather lurid, I apologise. This is a rather lurid screen dump from a newspaper cutting about Reliance's KG D6 gas field on the east coast of India. And just a few headline numbers, basically. At the time of this story, the field was producing 26 million cubic metres a day. It was supposed to be producing 87, so that's not a trivial shortfall. Reliance were fined $1.8 billion as a result of that shortfall to deliver the gas, which is interestingly quite close to the number that BP paid to enter, so I don't know whether BP just paid the fine or not. Perhaps that was the nature of the deal, I don't know. Gas fields have historically been seen as sort of simple, really didn't warrant a lot of detailed engineering or analysis. Actually, there's been a lot of development recently of deep water, offshore gas fields, normally pressured, and a lot of these fields have come a cropper on the back of water. There's been a tendency to sort of make the reservoir models too simple. The pressure depletes a bit, the water invades the well, very limited reservoir management, very limited intervention. That's what's causing disappointment in these sorts of assets, is a failure to sort of manage and predict water. And I think BG are seeing a similar challenge with their West Delta Deep asset, which is a 2 BCF a day, 10 TCF development feeding LNG, where they're having similar problems reaching their sort of sanction base case, predominantly on the back of reservoir complexity leading to water encroachment. And in a normally pressured well that is depleted, it does not take very much water to see the well off, basically. This is a little map of West Delta Deep. So this rather small map, rather underplays it. It's about 120 kilometres from the furthest subsea well to the beach. It's a full subsea development, and at the time, in terms of tieback distances, it was really quite leading edge. This little sketch here rather inadequately gives you a sense of the sort of subsea architecture. This thing was designed to do 2 BCF a day, half for domestic, half for LNG export, 100 kilometre tieback, further at the extremities. all subsea, 400 to a kilometre water depth. Multi-zone wells with open hole gravel packs. And this is another key issue, is a lot of these gas reservoirs are quite shallow, tertiary, quite friable. They tend to require sand control. Reservoir management in a multi-zone well with a large open hole gravel pack, well, there isn't any reservoir management because you probably never went in the well. You probably never gathered any data to find out what was going on. And even if you did, you can't do anything about it anyway. You would need to sidetrack the well and have some kind of zonal isolation. So these wells are not set up for reservoir management very well. Very limited intervention. The last time I looked at this project at BG, it had been on production for something like 9 years. There'd been 40 wells drilled, and the number of wells that had been entered was 0, not one well. Not one entry into a well to log for production. Now, actually in the last year or so, some of that work has been done. But when you compare that with a conventional platform-based development, with regular wireline access, your ability to understand the reservoir, to calibrate the reservoir is very, very limited unless you take quite, proactive steps in the development to acquire data and calibrate your models. This subsea architecture, when the remaining 20 to 30 wells have been drilled, is going to be quite complex. So you're sitting here in Idku, and a big slug of water or sand or silt arrives, and you then begin to scratch your head a little bit and think, well, I wonder at the end of this 120 kilometre network, which well did that? That's not a trivial task. So again, reservoir management in these fields has been quite a big challenge, and is part of some of the difficulties that BG is having at the moment meeting its contractual obligations. So not an easy system to manage. You need to be very proactive early on in the design of these facilities to allow you to troubleshoot, basically, to monitor and troubleshoot well performance. So just to round up the kind of second part of my presentation, and I'll endeavour not to fall off the step. So appraisal needs to deliver more value, and I think there's a tension here between what I call reservoir quantity and quality. So we heard earlier about explorationists. Explorationists are very difficult to get engaged in the concept of what a particular well might actually produce. They would just like to say, I found 7 TCF, I drilled some more appraisal wells, now it's 10. They're really not very focused on economic performance, they're focused on volume. And our appraisal programs are often not very good at teasing out the difference between the quantity of the field, its volume, and the quality of the reservoir, its ability for a well to deliver a volume of hydrocarbon. So my perception is that development well performance is really critical in project economics. And if you can afford it, and if you can make a case for it, then phase development, interference testing, extended well testing is the only way to get a handle on these dynamic issues, rather than fretting over the static. Now we have a bit of a problem here because we know how to do this. It's called a value of information analysis, yeah? Most of us will be familiar with that. My perception is that we know how to do the maths of a value of information analysis. We know all about Bayesian prior, and we know about probability trees. The problem is we're not very good at describing the uncertainties well enough to structure the value of information analysis to show that there's actually a case for doing something. So if I evaluate an asset and my uncertainty range is plus or minus 15%, well, I don't have much uncertainty. So it's very hard to show the value of this information. And I know the information costs a lot of money and it delays. So I don't think the problem with VOI is doing the maths. I think the problem with VOI is kind of structuring the uncertainties properly. And it's all very circular because we're doing this VOI analysis at the front end of the project when, of course, we don't know very much. So there's a real tension here between getting VOI to work properly and, and our tendency to sort of underestimate the ranges in these assets. Mega projects we've talked about. Resource uncertainty. There's nothing particularly special about the Deepwater. I think it's just that the bets are bigger. It's like going to a posher casino. The game we're playing of risk and capital management and uncertainty, stakeholder management, it's the same game. It's just there seems to be a 0 added on to the end of all the numbers. I talked a bit about reservoir management during the producing phases. There's a huge difference between your ability to acquire data and calibrate models and understand well performance in a scattered deep water subsea development that you'll probably never ever go into, and Brent Charlie, where you ran a production log once a week in every well and did TDT logging and that sort of thing. So we need to think about technologies that help there. And we're seeing some stranded gas, and there's no surprise here because, if you've got 1.3 trains of LNG, then you may as well have 0, because if you don't get to 2, then you can't move forward. We're certainly seeing longer time scales developing the market, and you need really, really good quality reservoirs to be able to afford to generate the lower cost base on gas that you're going to need to have. And personally, I would watch out for water in hydrostatic or normally pressured reservoirs. So we've heard a lot about how pace is what's creating a lot of these difficulties, and I don't have any difficulties with aligning myself with that, but my perception is that there's another sort of missing issue that we're not grappling with enough, and actually it's got nothing to do with deep water, it's got nothing to do with the oil and gas industry, it's just to do with the way people behave and interact. And a really useful book that I would recommend to any of you, in fact I wouldn't recommend the whole book, I'd recommend chapter 7. This is a good book produced by the SPE, by Begg and Bratvold on making good decisions. And most of it is about how to build a decision tree, how to do value information, how to do Monte Carlo modeling. But there's a really nice chapter 7, which deals with behavioral challenges in decision making. And I'm not going to summarize this in great detail. If you're interested, go and read the book. But it highlights a few key issues that make it difficult for people to make good, rational, objective decisions. And these boil down to a couple of issues. One of them, you might have seen this book, Thinking Fast and Slow. The guy won a Nobel Prize for it, so it must be a good book. It's about the way we think. And most of the time, we think in system 1, we think intuitively. Should I have 2 biscuits out there or 1? I didn't spend a lot of time thinking about it. I just intuitively had 1 biscuit. Our lives are so busy, we don't have time to sit down and rationally analyze what we should do all the time. Most of the decisions we make are instinctive, they're based on experience and intuition. That's called system 1. Some of us every now and then go, should I move house? Right, I think can I afford it? Where should I live? Where do we try to make rational decisions. So that's our reasoning part of our mind. And really, we ought to be in system 2 most of the time when you're trying to sanction a deep water project. And company processes and hierarchies and functional organizations are really a way to constrain people to behave in system 2 to sort of be objective and rational. The problem is we're all a bit lazy and we're all rather prone to sort of, staying in here. So we're sort of prone to making intuitive judgments, to being anchored by our history, that sort of thing. The other thing is availability, this is just really about vividness. And I think we had a point about that earlier when Mike highlighted the EWT. So the EWT on that project, it was right in their face, it was happening today, it was very available. So the team's perception of the project was very anchored, which is another thing I'll talk about, by that thing that was happening to them. It became the description of the field. Another one is anchoring. If somebody throws a number out there, these things have been studied exhaustively and extensively, and they're well-established phenomena. Is if I throw a number out and then I ask somebody else, there's a tendency to cluster around that norm. There's a really interesting study done where they stood outside a cinema and they asked people, how short was that movie? How short was it? Then they asked some other people how long it was. Now, they both watched the same movie, but the distributions of durations were statistically different in a significant way. So the way that you pose a question influences the answer that you give. We know well enough that we're consistently not having enough uncertainty in our estimation. And I think there's a huge human tension here, because if I'm paid a lot of money to spend 2 years doing a reservoir study, to then tell my manager that the uncertainty is plus or minus 60%, he might be reasonably, able to say, well, what have you been doing for the last 2 years? So there's a tendency that the more we study something, the more the uncertainties ought to reduce. But I'm not sure that's always clear. So we become anchored, actually. We become anchored to our models, and our uncertainty ranges tend to reduce. But the fundamental data might not have really have changed. You know, I may not have very much data. The seismic may be very poor. So who says the study is really helping us to reduce the uncertainty? And then the last one is group bias. And something I've been meaning to ask IPA for a long time, and I might do later on, is there any evidence that people do worse when they're on their own? Because my intuitive experience is that actually companies that go ahead at 100% working interest probably do worse than companies that behave in, you know, consortiums and do it. So if you don't believe any of this, that's fine. If you do believe it, perhaps a rather trite but useful example of it is this little, and some of you may have seen this before, but the question is, are the blocks A and B different or the same colours? Okay, so I've got A up here and I've got B down here. Now, if you want to get the answer to that, you have to go off to Wikipedia and have a little look, because I'm not going to try and convince you now because I usually fail. So I'll leave you with that as an example of bias and the way that we make decisions and make judgments rationally. And thank you very much for your time.